All right, now that we've learned all about our PV diagrams with our thermodynamic processes, now we're just going to do some practice with it to make sure you understand. On this first one here, I've got a situation where I've got a sample of gas where its initial pressure will define as P naught, initial volume as V naught, initial temperature as T naught, and it undergoes the following four processes. It's going to be heated at a constant volume until its pressure is 2P naught. Then it's going to be heated while keeping constant pressure until its volume is 3V naught. Then they're going to cool it down at constant volume until the pressure is back to the original, and then they'll cool it down at constant pressure until the volume is back at its original amount. So what I'm going to want you guys to do is attempt part A with part I on A, B and its three parts, and then C. I'm going to pause the video. I'm going to give you some time to work on it. When we come back, I'll just be doing one part at a time. So go ahead, give it a shot, and then we'll be back in just a few seconds. Okay, so if you take a look here with our graph, we have our pressure on our y-axis, volume on our x-axis, and I've labeled each of the steps and the temperatures that I've gotten. So when I look at constant volume, that means I'm going to be going straight up and down. I go from 1 to 2, P naught. Next step, constant pressure, meaning I'm going to go just horizontally, and that's going to be from 0 to 3 V naught. Same idea for these processes as we go back. Now, the thing that some of you may be wondering is, how did I get the temperatures? Well, if you think back to the ideal gas law, PV equals nRT, N and R don't change. So what that tells me is temperature is proportional to pressure times volume. In this case, since my pressure is doubling, volume is staying constant, that will be double, so there'd be 2 there, I'd have to put a 2 here. Same idea, I've doubled my pressure and tripled my volume, so that should be 6 times the initial. Then I go down here, initial pressure is the same, but my volume is 3 times as much, so my temperature should be 3 times as high. And that'll do it for part A. If you haven't yet done part B, go ahead and attempt it, and we'll be back in just a second to go over it. Okay, so I left a little graph up here so we can look at the process as we go through it. So part B, the first part of it asks, what is the net work done on the gas, meaning coming from the outside? So in the first step and the third step, you notice that if we label our axes here, volume doesn't change. And work is equal to pressure times change in volume. So these ones automatically have a work of 0. Next up, we have step 2, where our volume is expanding. Remember, when we expand, we're pushing out onto the world, meaning that's work done by the system, which means it's negative work done on. I'm not going to worry too much about the signs right now. You notice I put a negative there and a positive there. Just focus on the fact that it's work done on the system, meaning it's energy coming from the outside. And then for step 4, we're at a lower pressure, but doing the same volume change. Final minus initial volume for both of these. And on this one, I end up with negative. So in this case, let's just forget the signs. Let's just think about it logically. If I'm expanding at a higher pressure, there's more energy being done by that work. If I contract at a lower pressure, not as much energy is being done on me, meaning I'm not having as much pushed in, because you don't have to push as hard if there's not as much pressure. Meaning this guy is smaller than that guy, meaning more work is being done by the system than being done on the system. So this should be negative work done on the gas or positive work done by. You can put it either way. So you could write 2 P naught V naught, work done by the gas, or it's negative 2 P naught V naught on the gas. And this may be something that's confusing for you for a while. Just think of it this way. If you ever do a process at a higher pressure, it takes more or gives more energy. So if you go this way and then come, well, it's just like I said last one. On the, wait a minute, how did they say it? By the clock, on the counter. There we go. Got it. Next one we've got is asking about the internal energy change. Since it starts and ends at the same point, it's a completed cycle, therefore it's a Carnot cycle. And when we do that, by definition, we have an internal energy change that's equal to 0. And finally, we want to know what heat is added to the system. Since delta U equals 0, that means Q just has to be the opposite of whatever W is. Since this is work done by the system, we have negative work. We're losing energy. The system is doing more work than it is getting done on it. Therefore, we have negative. If we end up at the same temperature, that means we have to be adding heat every time that we go through. So we're getting work out of the system. This thing would be kind of like a car engine where you're getting more work done, but you have to add heat to make it run. So this would be heat added to the system. If you have not yet done part C, go ahead and do that, and I will be back in just a second. Okay, so for this last part, we're solving for the heat added to the system during step 2. That's the one where we are going from P2, or we're staying at P2 P naught, there we go, and going from volume V naught to 3 V naught. So this is an isobaric process, meaning that we're just doing work and there's heat added to maintain, we're starting that. Okay, now for part C, we're looking for the heat that we have to add during step 2. We know that our internal energy goes up because we go from a lower to a higher temperature. I believe it's 2 T naught to 6 T naught, meaning we know we have to end up with a positive value for this. We know that since the system is expanding, it's giving energy out. Anytime something expands, it's releasing. It's going to be a negative amount of work on the system. So we got to figure out what Q is. Well, we know W from part B1 is 4 P naught V naught. We know that's going to be negative because it's expanding. We don't know delta U yet, though. So we just plug it into our equation that we derived from the Boltzmann equation and the ideal gas law, and we get that U is going to be 6 P naught V naught. When we come down here, we rearrange the formula so that Q is equal to delta U minus your work. Since this is a negative number, that's the same as adding it. So what we end up with is that Q, or the heat added, is going to be equal to 10 P naught V naught. All right, we got a new problem here where we have a mole of 1 mole of ideal gas, and it's going to be taken through the following process. It goes from A, where it is at a volume of 20 cubic meters and a pressure of 200 pascals. It goes to state B, which is at a volume of 60 cubic meters, same pressure. Then we go up to C, where the pressure has now gone up to 400 pascals, but it's back to its initial volume of 20 cubic meters. And then it goes back to A. So what I want you guys to answer about it is, what is the temperature at point A? What is the net work when you go through the whole cycle? Is Q positive, negative, or 0? And is our delta U positive, negative, or 0? So take a second, go through the problem. I'm going to pause it just like I did with the last one and go through step by step. Make sure you try them out before I go through them. On the first step here, since I know it's 1 mole of an ideal gas and it's an ideal gas, I can just use the ideal gas law. So I plug in PV equals nRT, pressure, volume off of the graph, R is a constant, 1 mole is all we're using, and when you solve for that, you get 281 Kelvin. So now go ahead, try part B, and we will be right back with the answer. All right, so for part B, we're trying to find the net work of the process. In this first process, our volume is expanding. So when I go from A to B, I'm going to be doing work. The system is pushing out, meaning it's losing energy. So I'll have negative work, I'm expanding. So that's what the area under the graph looks like. For compression, that's step BC, where my volume is getting smaller, but I'm increasing pressure. This is going to be my positive work. For C to A, no work is done because I'm at a constant volume. So what you're left over with is negative this plus positive that gives me this triangle. Triangles are nice and easy to use. It's just 1/2 base times height. So I do 1/2 60 cubic meters minus 20 times 400 pascals minus 200 pascals, and what I'm left up with is 4,000 joules. Now I'll go ahead and solve parts C and D because they're going to go together with this. So on C, it's asking you to find out whether or not Q is positive or negative for the whole process. If you look at the chart, we automatically know part D, our answer, delta U equals 0, because it starts and ends at the same point. So if delta U equals Q plus W, and this is 0, and my work is positive. So this guy's positive. What does that mean Q has to be? Q has to be less than 0, meaning we have a negative Q. Cool. We got one last more to do before we are done with these practice notes. On this last one, we have an ideal gas undergoing the following. From A to B, it's slowly compressed from 10 to 1 liter while maintaining a constant pressure at 1 atmosphere. From B to C, your volume is held constant and heat is added so that pressure and temperature can rise until pressure is equal to 10 atmospheres. And then while your temperature is held constant, it returns to its initial pressure of 1 atmosphere. What I want you guys to do for part A is sketch the cycle. For part B, to determine the work done for A to B and B to C. And then at the end, you will have to find the heat for the process, the total heat added or removed from A to B to C. So that whole process combined. One thing I will warn you is you won't always get straight lines, so be aware of that. Okay, so for part A, I have plotted my cycle here. From A to B, constant pressure, but volume is being compressed, so it goes like this. Then I have a constant volume, and then change my pressure. Just goes straight up to C. And then this is the one that was a little tough. The hint should have been that the temperature is maintained constant. From C to A, I go through an isotherm. So remember, isotherms are those curves that we see on a PV diagram where everything else is held constant other than pressure and volume. So now that we've got that, go ahead and attempt part B, and then we'll go on to part C. Okay, so for part B, we're looking at the work that is done by the system. From A to B, we're undergoing compression, meaning that we're gaining energy. Energy is being added to the system, so we should end up with a positive number. Remember when we do work calculations that we need to have them in our base SI units, so we need to be in terms of cubic meters for volume and pascals for pressure. Our pressure is 1 atmosphere, so 1 atmosphere is equal to 1.013 times 10 to the 5th pascals. Then for liters, the conversion is 1 liter is equal to 1,000th of a cubic meter. So when we're down to part B, we should be at 10 to the minus 3, and then 10 times bigger than that should just be 10 to the minus 2. So we're going from 10 liters down to 1 liter. When we multiply those two together, we end up with 9,117 joules, and that's positive because it's being done on the system. And then for part B to C, there's no volume change, no work. For this last part, since we know that from C to A, we are on an isotherm, which means that there's going to be the same temperature at the beginning and end, it tells us that TA equals TC. So our delta U for that process from A to B to C has to be 0. If you end up at the same temperature, you have no change in internal energy. That means when we set up our first law of thermodynamics here, we know delta U equals 0, so Q is just the negative of our work. Since our work is done on the system and it's positive, that means we needed to release 9,117 joules of heat as we go through the process. That's going to be it for our thermodynamics PV processes. If you're still having trouble with this, just let me know and we can go over some more. Or if you're going through the homework and have trouble, just give me an email.